Hello, I'm Josephine Kalimbi and I'm going to be presenting the fundamentals of AI. So, the origins of AI and the milestones. So, artificial intelligence began with symbolic approaches, and these were systems that used explicit rules and symbols to represent knowledge. This was dominant between the 1950s and 1980s. However, in 1974 to 1980, the AI experienced its first winter, and this was a period of fu- reduced funding and interest due to unmet expectations. In 1980, however, expert systems emerged, mimicking human experts by encoding domain knowledge. These historical shifts are important for our project because they help us build it. So then we have the current and future trends. Today, AI is transforming fields like natural language processing, healthcare, and self-driving cars. In healthcare, AI supports diagnosis, prediction, and personalized care, which are exactly what our project, the Conceive Score, aims to do. Looking ahead, trends like general AI, ethical safeguards, and explainability, and human AI collaborations will be critical. Then, for data mining evolution, AI has evolved from symbolic rule-based systems to statistical models and now deep learning. Symbolic systems were rigid, the statistical models introduced probabilistic reasoning, and the deep learning brought adaptive predictive capabilities. Then the types of intelligence, we have the logical mathematical intelligence that powers reasoning and algorithms, which are essential for calculating conception probabilities. Then we have the linguistic intelligence um, with the natural language processing, translations, um, like chatbot interfaces or voice assistants. So, in philosophy, we distinguish weak AI tools that, and these are weak AI, and these are tools that simulate reasoning, then from strong AI, which implies consciousness. Our project, the Concept Score, is a weak AI system because it supports decision making but does not understand fertility. This distinction helps us manage expectations and ethical boundaries. Then we have relating it to our project. Our project shifts from symbolic calendar methods to statistical fertility models. We use logical mathematical reasoning to calculate probabilities based on age, cycle length, and other features. Then we have linguistic intelligence that could help explain results in natural language, making the system more accessible. Then, most importantly, our project um, fits in as a weak AI because it does not weak AI because it supports decision making but does not understand fertility. This reinforces its role as a tool, not a replacement for clinical judgment. So AI problem solving involves three components, and these are initial state, operators, and a goal state. In our project, the initial state is the patient's fertility profile, then the operators are the statistical rules and transformations we apply, then the goal state is the um, personalized conception likelihood. Our system finds the optimal path, the best combination of factors to support fertility decisions. Then we have the problem solving by search. AI uses search to navigate complex problems. And informed search includes the breadth first and the depth first methods. These are useful for exhaustive explorations. Informed search uses heuristics and algorithms to prioritize promising paths. Our project, which is a concept score, uses heuristic search to prioritize factors like age and helping clinicians focus on the most influential variables. Then we have application. In our project, heuristic search helps prioritize conception factors. For example, age and cycle length are weighted more heavily than other secondary features. Then, um, search methods also support resource allocation, helping fertility counselors decide which interventions to prioritize based on predicted outcomes. Then we have the knowledge representation. Symbolic AI represents knowledge using semantic networks, forms, and first-order logic. These structures help encode rules and relationships. In our project, the concept score, we use structured rules to represent fertility knowledge. For example, linking age and cycle length to conception probability. This symbolic layer ensures interpretability. Then we have application of that. So we have rules like if the cycle length is greater than 26 and the age is if the cycle length is less than 26 and the age is less than 35, then probability conception are encoded. Yes, then probability conception might be higher than if irregular cycles and age is greater than 40, then we might put it to lower probability. These rules are transparent and clinically intuitive, and they allow us explain predictions clearly. And we have inference in the first order logic. So inference involves deriving conclusions from known facts. Then soundness means every conclusion is true if a certain premise is true. Then in the concept score, then we have completeness, which means the system can derive all valid conclusions from available knowledge. So in our project, we ensure soundness by using validated clinical rules, completeness by is supported by covering a wide range of fertility scenarios. Then we have application of that. For example, if a patient is under 35 and has regular cycles, um, our system infers a higher probability of conception. Then, if cycles are irregular and the age is over 40, the inference shifts towards lower likelihood. These logical steps are transparent and clinically grounded, supporting trust and decision making. Then reasoning and uncertainty. The real world data is usually noisy and incomplete. So Bayesian reasoning helps us update probabilities as new evidence arrives. Probabilistic models like the Bayesian network represent dependencies, for example, how age affects psychoregularity and perception likelihood. So our project uses these models to handle uncertainty and provide robust predictions. Then we have planning. Um, Planning in AI means creating a sequence of steps to reach a goal. In our case, the goal is to support conception. Our project by Concept Square uses frequent patterns like length and age to guide what actions come next. For example, if a user has regular cycles and is under 35, the system might suggest tracking for a few months before clinical referrals. This planning process helps structure fertility support over time, making it more personalized and more efficient. Then we have planning and decision making. AI does not just plan, it also makes decisions by weighing benefits and risks. Our project at Francisca does this by combining predictions with decision rules. For instance, it may recommend lifestyle changes if the predicted conception likelihood is moderate, but suggests clinical intervention if it's low. It considers the patient goals and restraints like age or access to care. This balance between utility and risk helps the system offer more relevant advice for each user. And lastly, we have machine learning that helps a concept score learn from data. We use supervised learning to train the models on labeled fertility outcomes to predict new ones. For example, the system learns from certain cycle patterns and age ranges that these are linked to higher conception rates. And unsupervised learning could help us group users with similar fertility profiles. Together, these methods allow the system to recognize patterns and make accurate predictions. All this based on real-world fertility data.